Now let's learn about the few things about the adiabatic principles in hydrogen molecule. So hydrogen molecule is the simplest system. The adiabatic principle is also called Born Oppenheimer principle. Which is the simplest system and where we have vibration of ions and electrons. So basically we have two protons and one electron. One electron. Let's suppose the distance between the two two ions of hydrogen is given by r vector, and the distance between the center of mass, this is the center of mass here, center of mass, and the distance between the center of mass and the electron is given by small r vector. This is electron basically. So we don't study of these molecules, that is hydrogen molecule without an electron. So that is, we don't study the movement of this molecule around the center of mass. We just study the internal motion. We just study the internal motion. We just study the internal motion, that is vibration. So the important thing is that the position of one atom with respect to the other and the position of electron with respect to the center of mass. So center of mass is in the middle, as you can see in the diagram here, as the two atoms are equal. So since we are studying only the internal motion, then basically instead of using the mass of H plus or H minus ion, we use the reduced mass concept, which is equal to m by 2. So this is the reduced mass, and this is the mass of the ion. So what is the quantum operator for the given system? So the question is, what is the quantum operator for this given system? So it is the kinetic energy of the electrons. Let me write. It is the kinetic energy of the electrons, and the Laplace operator for the position of the electrons, and kinetic energy of the ions, in which we have Laplace operator for the position of the ions, and we have interaction between the electron and nucleus. We can write in this fashion. Let's continue from below. And we have also the repulsion between the electron and nuclei. Okay. So we can simplify by writing in this fashion. This is the kinetic energy of electron, this is the kinetic energy of neutron, plus potential energy between the electron and nuclei, plus potential energy between the nuclei. Now the first approximation is to separate this study. Let's consider the ion system is frozen. So the idea of adiabatic principle is that the mass of electron is much less than the mass of the nucleus. So the electrons are very fast. So if we move the configuration from its initial position to the new position, then the wave function of the electrons will adapt immediately to the new position or situation because the inertia of the electron is less. So we can study what are the wave function for the electrons for a fixed position of the nuclei and use this as a parameter. So basically we will solve the electronic problem, that is frozen electronic problem. So we use only the operator of electron, that is, so in this expression, so in this expression we are going to use only the operator of electrons, that is this operator and this operator, which is equal to the H naught plus T and N. So H naught is the Hamiltonian only for electrons, and also we find the solution for this equation. So here alpha is the quantum number for different atomic levels. So remember that this is not the exact solution. Now we want to find the exact solution. So real problem is the total Hamiltonian, and we want the total wave function of the electron with respect to the nuclei. That is total Hamiltonian, total wave function of the electron with respect to the nuclei. So now we use superposition principle, because if we consider all the set of eigenfunction of the Hamiltonian operator, we can always write any other function as a linear combination of psi alpha. That is, we can write the total wave function as in this fashion. So this is the electronic solution. This is the electronic solution, and this is the some coefficient alpha, which some coefficient phi which depend on r vector, and which is the parameter of the problem. So the original problem is to find this thing. Now the problem is to find this thing. So we just change the problem. So in order to solve, we put this in the equation of in this equation. So if we do this, which is the crucial point, we get a very complicated equation in which all the phi alpha with different phi with the different alpha are coupled together. So it is very difficult to solve. So basically we are using the adiabatic approximation. So basically the adiabatic approximation separates the ionic problem, and the electronic problem, But if we neglect some non-adiabatic terms, we find the easier equation in this fashion. So it means that we can decouple all alpha. So what is this solution where we have only one alpha? So it is a solution and it can be represented as total wave function is equal to phi alpha psi alpha. So here phi alpha is the wave function of nuclei. Wave function of nuclei. And phi alpha square is the probability that the nucleus is at distance r, that the nucleus is at distance r. And here psi alpha square, mod of psi alpha square, is the probability for a nuclei. So how do you find the wave function for the nuclei? We will write this Schrodinger equation with kinetic energy, potential energy plus the electronic energy, which corresponds to the effective potential energy. That is, effective potential energy system is given by in this fashion. Yeah, so this is the representation of the effective potential energy. Effective potential of the nuclei. So we have a molecule because electrons in between them are like glue. So the electronic energy has the role of potential energy attractive for the nuclei. So we neglect non-adiabatic terms because mass of electrons is very, very less than the mass of ions. So let's know about the condition for neglecting the non-adiabatic terms. The problem is that when you apply total Hamiltonian operator to this expression, when you apply the nuclei kinetic energy, which contains the Laplace operator r vector, when this is applied to the total wave function, we have this expression. So it is observed that from this equation that this operator acts only on phi n, that is nuclear wave function, not on electronic wave function, that is psi n. So the electronic wave function psi n depends on r vector, but also parametrically depends on the capital R vector also. So that is psi n is the function of both small r vector and capital R vector. So the above equation is not true because Tn acts also on psi n. So when you consider psi alpha as in this fashion, as a constant with respect to the kinetic energy of the nuclei, that is Tn. So when the dependence on r vector is very weak, so this dependence is very weak. So the dependence on this capital R vector should be weak. So we can write the equation in this fashion. Now we want to study. Now if we want to study the dynamics of ions, we have to consider the effective potential. That is, this potential we have to consider, which includes the electronic energy. So a further approximation is that when you assume the potential as a parabola, the effective potential is looks something like in this graph. Um, this is R and this is the effective potential, and the effective potential looks something like in this fashion. Okay, so if we study this small vibration around the equilibrium position, which is this one, the equilibrium position is this thing. This is the equilibrium position. So if we study the small vibration around the equilibrium position, this is equivalent to approximate this potential to the second order, which is the further equivalent to having spring between the nuclei. That is, spring potential can be given by this expression. Spring potential. Now let's do for the electrons in a crystal. Let's write our Hamiltonian operator for the crystal. So let's consider the simple crystal without a basis. So here Hamiltonian operator is given by kinetic energy of the electrons plus kinetic energy of the neutrons plus interaction between the electron and nuclei plus interaction between the nuclei and nuclei plus the interaction between the electron and electron. Okay, so this is the Hamiltonian operator for all crystal, that is electrons plus ions. Now let's write the position of nuclei. Consider the atoms here. So imagine this is a Bravett lattice. So imagine this is a Bravett lattice, and we have the lattice position indicated in this fashion. So this is the lattice position and vector, and if the ion can move, then here this un vector is the displacement from initial position to the position n. So the position of ion is given by this is the Frozen position, and this is the displacement. So this can be a vibration. This displacement can be a vibration. Now let's write the kinetic energy of electrons, kinetic energy of neutrons, and rest of the other expressions. So let's assume that Ri is the position of electrons, and now let's write the expression here. Kinetic energy of neutron is given by this expression. Kinetic energy of neutron is given by this expression. Potential energy between the electron and electron is given by this expression. and potential energy between the electrons and neutron is given by this fashion. And the potential energy between the neutrons and neutron is given by this fashion. This is the position of first atom and this is the position of second atom. So it's complicated and we want to find the total solution. So the wave function depends on all the positions. So the wave function depends on all the position of electrons and all the displacement of atoms. So this is total wave function, which depends on all the position of electrons and all the displacement of atoms. So it is a wave function with many variables. So for simplicity, let's write in this fashion. Now we will do the same as we did for hydrogen molecule. First, we will solve the electronic problem with a frozen crystal, and we will write this thing. So just notice the electronic part of the Hamiltonian. So we will find some electronic wave function with some values of energies. So let's solve the electronic problem given by this equation. So we are solving the electronic problem with a fixed situation and we will find the eigenvalue of energy for the fixed position. So now here comes the important point. The solution is the almost equal to the solution when all the displacements are zero. That is, so it is true that the vibrations are very small. That is, the electrons don't care if the atom is exactly in position or not. So the atoms are in Bravais position. So if we can use this or assume this, then we can use Bloch theorem. The adiabatic approximation is equivalent to the fact that electronic function depend weakly on the position of the nuclei. That is this position. So now we want to solve the problem. Now we want to solve this problem. That is we want to solve this problem. So we write total wave function as a linear combination of some coefficient which depend only on all the displacement of ions multiplied by the electronic function. That is in this fashion. Now we put the above equation in this equation and we neglect some non-adiabatic terms. That is, the mass of electrons is very less than the mass of nuclei. So what you get is the equation for phi, that is the wave function of the ions. So the equation we get is this equation. So for the equation, we find the eigenfunction of the ions and we find the total energy. So we see that the real interaction between the ions plus the electronic energy is like an effective interaction between the potential. That is, effective interaction between the potential is given by the real interaction between the ions plus the electronic energy. So the electronic energy plays the role of effective potential energy of the ions. So if the vibrations are small, we can approximate this as in the second order. So this is equivalent to say that all atoms are connected by springs, um, and quadratic approximation means connecting by springs. So E total will be the sum of electronic energy and vibrational energy, and the vibrational energy will be quantized. So now neglecting the non-adabatic terms, it is equivalent to say that this equation is true. So for each electronic state alpha, we can find many solutions of the vibrational problem. So we had two set of quantum numbers, that is alpha for the electronic problem and beta for the ionic problem. So the question is, what is the quantum number beta if we have an harmonic approximation? So it will be the quantum number of harmonic oscillators. So for each vibration, we have quantum number which says what is the vibration level of those oscillators. So the problem is that the harmonic oscillators that we will find are not the single atom. We have collective vibration. So what are the harmonic oscillator that we have to consider? So we have to consider the normal mode. So this is the topic of our next lecture, in which we are going to introduce the concept of the normal modes for a crystal. So for now, thank you.